Okay, so 5.1b, we're going to start talking about decay models. And that's, decay is when you're starting to lose things. So example 6 says, okay, it pays to advertise. It's frequently true that the weekly sales will drop rapidly for many products after an advertising campaign ends. This decline in sales is called sales decay, which just really seems weird. I mean, really, if Coca-Cola does not advertise, their sales go down? I mean, I don't even think about, oh, I saw that on a commercial, I'm going to go buy Coke. No, I'm just in the store and I see it and I buy it, or I'm at McDonald's and I see it and I buy it. Anyway, maybe it affects me more than I think, or maybe it doesn't affect me at all. Don't know. But they give us this formula for a decay model for this particular advertising campaign. And S then tells us how much money we're going to lose if we don't advertise. Okay, where X is the number of weeks after the campaign ends. So, for example, what is the level of sales, A, when the advertising campaign ends? So how much time has gone by? 0 here. So we're going to put a 0 in there. So that means 0.5, negative 0.5 times 0 is 0, and 2 to the 0 power, any number to the 0 power is 1, so $1,000. Okay? So S is just $1,000 because this all cancels out to be 1. B says, what is the level of sales 1 week after the campaign ends? So all we're going to do here now is, it said that X represents the number of weeks. So we're going to put a 1 there. So we're going to take 2 to the negative 0.5 times 1 power, or just negative 0.5. And when we do that, we end up with $707.11. Okay, so key thing is to know how to do your exponent thing. So what I would do, I would take negative 0.5 times 1, which obviously is going to be this, and then you're going to use the keyboard. I wish I had a picture of a calculator. I think I do have one on my phone. Let me see what it is here. It is a key that looks like this. Okay, so then you put 2, hit that key, and then negative 0.5, put enter into that, and that will give you 2 to the negative 0.5x. Okay, if you're still having a hard time trying to figure out what the heck do you do there. Okay, use the graph of a function. Okay, I'm not going to worry about the graph. You can look at that. According to this model, will the sales ever fall to 0? Well, one of the things that you'll notice here is never will this particular exponential function, when they graph it, they get a graph that kind of goes like this. And it will never, when it does that, and it shows that in the graph, it's never crossing the x-axis, which means it'll never cross 0. Okay, so next section. And this section is kind of nice because I've taught this before in other books, and they just spend so much time on this that it just drags on forever. And fortunately, this book doesn't do that. We can get into some real stuff. So, the next section is called the number E. That's kind of a weird way to say that, isn't it? It's kind of like the color 9 from a song that I used to listen to. Anyway, E is a number or a symbol that represents the number 2.71828, and then it just kind of goes on and on forever. Okay? So that is the base. So rather than write this number every time, they just use the letter E to represent that number. Okay? So that really helps, and E is a lot easier to write than some big old herkin long number. So let's look at an example here. Oops, sorry, my thing keeps turning around for me. Let's look at example 7. They use the formula P, and then they've got the E, and then the R, rate, T, time. This is the principal. So let's say that you're putting some money in the bank, and you're putting it in there for 15 years, and it is being, the interest rate that they're giving you is 10%. Whoa, that's a lot, really. Okay, so you're putting it in there for 15 years. We're going to use this formula, and we're going to plug some numbers in there. I want to find out how much money I'm going to have. So I put $10,000 in. That's my P. My E, then, I'm just going to leave that because your calculator should have a button that looks like this. So you don't have to put that number 2.71828. The calculator already do that. And the rate is 10% or 0.1. And the time is 15 years. Okay, and that was taken from that. So, multiply those two. And what you're going to do is you're going to push, you're going to take 10,000 times e to the 1.5. And the way you take e to the 1.5 is you plug in 1.5, then you hit the e to the x button. Okay, so you put your exponent in first, then you hit the e to the x button. And some calculators, I know my calculator has a button that says LN, and then there's an e to the x above, so you have to hit the function or the shift button in order to get to that key up there. But anyway, that's the way you do that. And you should end up with $44,816.89, which brings us to our final example, which is example number 8, having to do with carbon-14 dating. And this is used a lot in story problems, the carbon-14 dating. And basically what carbon-14 is, when an organism dies, the carbon leaves whatever the living organism is, and it gradually gets lower and lower and lower, and they can find out on how much carbon is left in that dead creature, how long ago it lived. And they use just all kinds of different things, I guess, in order to do it. And anyway, the function for this is just kind of weird, and it looks really hard, and it's not. Okay, so there's the formula. So what you're going to do is, it says in A, under example 8, if the original amount of carbon-14 present in an article or in an artifact is 100 grams, how much remains after 2,000 years? So our time is 2,000 years. So we're going to put 2,000 years in there for t, multiply it by this whole thing, don't forget the negative, and then we're going to use our e to the x key to get this part of the problem. Now, what about the YO? The YO is the original amount of carbon-14. So that number is going to be 100. So we're going to get 100, and we're going to multiply it by e times, or e to that power that we had up here. And I don't know what it is off the top of my head, but we find out that that number is similar to 78.5 grams, which means after 2,000 years, we should have 78.5 grams left if we started with 100, which is what I don't understand about carbon-14 dating. How in the world do you know how many grams you started with if all you know is what you've got left after a certain amount of years? I mean, if you found something in the woods and it had 10 grams of carbon-14, I mean, I don't know how old it is because I don't know how much it originally started with. But anyway, that's just me. B, what percent of the original amount remains? Okay, so we're still using that same formula, and it says what? after 45 years. So we've got f of 4,500, that's how many years, equals, and we're going to leave the y(o) by itself because that's the original amount. That's what we're looking for in this problem. And then we've got e to the negative 0. That big old long Herkin number. And we have our time being 4,500 years. And that gives me 0.58. So that means there's 58% of that remains after 4,500 years. Okay? So maybe that's how they do it. Anyway, that's 5.1. So only took 2 videos for that.